Okay, so what we'll do is we'll quickly go through the solution here, and then we will discuss things in detail. So we know that when the planet is in the perihelion, in which case the distance between the planet and the sun is minimum, we know that the corresponding velocity would be maximum. And when the planet is at the position of aphelion, the, which means the distance between the planet and the sun is maximum, we know the corresponding velocity would be minimum. Right? So minimum distance, maximum velocity, maximum distance, minimum velocity. And since this movement of planet around the sun obeys the law of conservation of angular momentum, we know that momentum at aphelion should be equal to momentum at perihelion, or the other way around, and which is equal to velocity into distance at that position and corresponding velocity distance at aphelion or perihelion. In this case, L1 is Vmax into x1, which means we're talking about perihelion here, and at aphelion it is Vmin into x1, right? Maybe I should write this better as angular momentum at perihelion is equal to angular momentum at aphelion, right? And therefore Vmax into x1 is equal to Vmin into, my bad, this is not x1, this is x2. This would be x2 here, yeah. So what is Vmax? V0 times x2 by x1, which gives us the correct option as option D, V0 times x2 by x1. So very straightforward question. Now, to make sure that we understand the concept in a better way, some of us here might be confused with the terminologies used here. So first let us see what is a elliptical, what is an ellipse for that matter. So ellipse is a two-dimensional figure that is carved out of a cone, or in other words, this is a conical section, right? A conical section. Now, how do we get ellipse? How do we get a circle? And the exact method of getting the section is something that we probably we will have to discuss a lot of it if we are discussing conic sections of maths. Since this is not conical section of maths, let us not spend much time there. So just understand that ellipse is a conical section of ellipse is a conical section. Now, once we know what is ellipse, let us quickly go through the given question. A planet's minimum and maximum distance from the sun are x1 and x2. So it is not given here that the planet is in elliptical motion. Yes, no doubt about it. So I have assumed here that this planet is Earth. Okay. And Earth is in an elliptical orbit around the sun. And if I were to, if I were to give a broader classification of this question, this actually is not a question based on Kepler's law. This should primarily be fitting in law of conservation of angular momentum. But many of the textbooks have classified this under gravitation. That's why I've just pulled up this question here. So we know that the maximum distance is x1 and the corresponding velocity would be minimum v0. When the distance is maximum at x2, the corresponding velocity would be, when the distance is minimum x1, the velocity would be maximum, and when the distance is maximum x2, the velocity would be minimum at v0. Okay, so x1 corresponds to v1 and x2 corresponds to v0 here. All right. Okay. Now, what is the ellipse? So this represents the ellipse here. We have a major axis, the minor axis, center with the formula x square by a square plus y square by b square is equal to 1. which has two focus 1, two foci, focus 1 and focus 2. And we also have to understand this phrase, eccentricity. And how do we understand that? What is A and B? I'll come to eccentricity in a while. What is A and B? This coordinate, minus a comma 0 plus a comma 0 represents A. What is B? B 0 comma B and 0 comma minus B. These 2 points. And we have another point, minus c comma 0 and c comma 0, which represents the two foci. 0 comma 0 is the center. What is eccentricity now? So this would give you an idea about how eccentricity varies, and how the figure of the visual representation of the figure varies with respect to the centricity. So when e is equal to 0.95, we have a very close ellipse, and when it's almost equal to 0, we get a circle. And we get only one center when eccentricity is almost equal to 0, and when eccentricity is almost equal to 0.95, what we get is the presence of two foci. Okay. To give you a better idea, when eccentricity is 0, we get a circle. When it is infinite, we get a straight line. Equal to 1, ellipse. Equal to 2 is hyperbola. Okay. Well, again, these are topics that you would have already dealt in detail in conic sections in your class 11th maths. Now, what would be the key difference between orbit if it is a zero eccentricity orbit and a high eccentricity orbit? If it is a zero eccentricity orbit, then the motion of the planet around the sun would be in a circular path. Maybe I should write it down here. It should be around a strictly circular path. Whereas in this case, it will be a elliptical orbit. Okay. Now, these days are really important. 3rd of January, July 3rd. It is, well, I shouldn't be writing the exact dates. That doesn't matter here. Okay. So the dates at which Earth comes to perihelion, which is closest to Earth, Sun, and aphelion, which is farther away from the Sun, is important. Definitely not in this question. So, in this year, 2025, Earth was closest to Sun on January 4th, 2025. It was very recent, July 3rd, that the Earth was at the perihelion. The aphelion. Okay. So let's just try to understand it one more time. Aphelion is the maximum distance, which is 152 million kilometers. Perihelion is the closest distance, which is 147 million kilometers. So yes, a difference of 6 million kilometers between perihelion and aphelion. Now, why are these dates and why are these important in general? Because of, okay, let's not go into that. Because of climatology, weather phenomenon and all these things related to geography. Let's not discuss that here. Maybe when you follow my lectures on geography and civil services. Okay. Now, what's the difference between aphelion and perihelion? Perihelion means peri is near, helio is sun, so is near to sun. Aphelion is away from sun. Okay. Just to make sure that you get a crisp idea of this. If you want to write it along with me, maybe you can just take down this diagram. So the orbital speed is fastest when it comes to perihelion, and it is the slowest when it comes to aphelion. So farthest position, the orbital speed is slowest. Closest position, the orbital speed is fastest. Time of year, roughly early January, early July. And in both positions, even though the orbital speed is different, what remains the same? Exactly, the angular momentum. Okay. So when perihelion is the position of Earth, when the distance is minimum, velocity is maximum. And when aphelion is the position of Earth, the distance is maximum and the corresponding velocity is minimum. Okay. Now, what is the implication? So when we consider the system, which becomes really important while you explain any of your processes based on law of conservation of angular momentum. So here the system is Earth-Sun system. So when you consider Earth-Sun system, essentially what we're trying to say is the net external torque acting on this, is equal to 0. Right? And this motion is completely under the influence of which force? Under the influence of only one force, which is the force of gravity. Right? Now, what is torque? Torque is defined as R cross F. Now, why are we talking about torque? Because law of conservation of angular momentum applies only when torque, the net external torque, is equal to 0. Right? So, what is torque? Torque is defined as R cross F. What is R? Again, vector R cross vector F. Now, what is vector R? It is a position vector. What is vector F? It is a gravitational force, which is again a vector. So, gravitational force originates from the Earth. It is pulled towards the Sun. Right? Therefore, base, head. Position vector, initial position vector, final position vector. Oh, well, okay, that's the wrong way to say that. The position vectors from the Sun to the Earth. Right? So, what is the angle between these two? So, the angle between these two vectors here is theta is equal to 180 degrees. Right? And when theta is equal to 180 degree, what is R cross F? R cross F is equal to RF sine theta. What is theta? Theta is 180. So, this becomes sine 180. And how much is sine 180? 0. So, this becomes RF times 0, which is 0. So, in this case, torque is equal to 0. Right? So then you might actually come up with a question here. I mean, you might be curious to think of this. If the net external torque acting on the Sun is equal to 0, if the net external torque acting on Earth is equal to 0, then how on earth is it spinning? Right? So that's one question. Probably should be the food for your thought for the day. Maybe you can think of it more. Right? Okay. Now, in our case, when the net external torque acting is equal to 0, we know that the angular momentum is conserved. And what is angular momentum? Angular momentum is the product of mass and its angular velocity, which is linear velocity into radius. So L is equal to mvr is conserved, which means L1 should be equal to L2, which means L initial should be equal to L final, which means L aphelion should be equal to L perihelion. Hope that makes sense, right? Now let us just try to bring these two concepts together. So law of conservation of angular momentum: if no external torque acts, then angular momentum remains constant. Excuse me. And since r vector and f, which is the position vector and the gravitational vector, are in the No. It can't be. It can't be said to be in the same direction. It has to be in the opposite direction. The angle between them is not 0. It is 180 degrees. Therefore, r cross f is equal to 0. Please, there was a minor error while I typed this up. Sorry. This actually is. It means r cross f is equal to 0, and therefore no external torque acts on this. And since there is no external torque acting on this, the angular momentum of this planet about the sun should be conserved, which this case is Earth. So if no external torque acts, we can therefore say that the angular momentum remains constant, which means when the Earth is closest to the sun at perihelion, the velocity should be large, and when the Earth is farthest from the sun at aphelion, the velocity should be small. And angular momentum at perihelion should be equal to angular momentum at aphelion, which gives us v1 times r1 is equal to v2 times r2. Therefore, v of perihelion is equal to v of aphelion times radius of the distance at aphelion by distance at perihelion. Okay, so that is how we come to this formula in two different ways. Actually, it was not two different ways. I was just trying to give you the explanation in two different ways. So I hope you get the clear-cut idea now, right? So the key takeaway from this question is law of conservation of angular momentum 1, and the angle between radius vector and the gravitational vector, which makes the net external torque is equal to 0. Okay. Now there are a couple of more questions which actually would test your knowledge on these concepts here. How is the angle 0, and what if the angle is not 0, and such hypothetical statements. Okay. Moving on to the next question. Oh, that's immediately a question which is based on statements. Very good. Let's try to solve that. Which again is something based on movement of a planet